So we're going to just start where we left. We had how to describe operators in terms of permission operators and their correspondence with the wave functions psi and different properties, how we could map or identify observables vis-a-vis those operators. So continuing with that, we are going to have, so we just try to see how we can have some of the relations like uncertainty relation, I think, and in this formalism of the thing. So if you remember that we know an Schwarz inequality for two states, Schwarz inequality for two states psi and psi prime can be psi prime psi is is less than or equivalent to the inner product of psi with psi prime with psi prime, as well as psi with psi. And the corresponding generalization is such that the cos square theta can be less than or equivalent to 1. So this inequality can also be proven if we are going to use our previous understanding that, for example, if we introduce psi prime as psi minus, so it's the original state, the full Hilbert space, how we can construct it from the Hilbert space, which may or may not be complete in that sense. So if psi is so you can have psi can be defined as psi as components of psi prime is psi, modulus of psi is psi prime is psi. So you can write it that, and we note that it should be less than or equivalent to 0, should be psi prime interproduct with psi prime and psi of with psi. So it will be, if we have all the things, this with this, so it will have 4 terms. So we are going to just see it, 2 of them will cancel. So at the end, so you will have like this psi prime, psi prime minus twice psi of psi prime, psi prime psi, and psi square, psi prime psi square. So you can write it in terms of, you can write it as psi prime minus psi prime square. Now to have a precise, how we can have a precise definition of an uncertainty principle, we are going to write expectation values of this Hermitian operator A, Hermitian operator A, we're going to write from its expectation value. So we are going to, we write Hermitian operator A from its expectation value with state represented by psi. So earlier we had a correspondence of this Hermitian operator and this psi observable Now we are going to write Hermitian operator from its expectation value with the strict psi. So expectation value, you can define it as root of this is difference of the two difference of a minus square of the expectation psi. And for the purpose of convenience, we can rewrite this delta psi. A can be written as psi A psi, and where psi E can be written as A minus expectation value psi of this is root of psi. So now for any pair of Hermitian operators. Now if you have two Hermitian operators A and B and use for any pair of Hermitian operators A and B, and using this Schwarz inequality of maybe this inequality. So we are going to use this inequality here. So delta psi A, delta psi B. So for any two operators, for any two pairs of Hermitian operators A and B, so it will be greater than or equal to psi A, psi B. So the scalar product on the right hand side can be expressed as scalar product on right hand side can be written as, so this is so it's, we have flipped it, this is so we have flipped it, that's why it's greater. So scalar product on the right hand side can be written as, so psi A psi B can be written as psi of so we have defined A minus expectation value of A, so this is 1 for 1, and for this B it will be psi of B minus expectation value of B into psi. Oh, sorry, and denominator it's psi. So what we are going to use, a particular property which we have been using throughout, that psi of A B psi conjugate will be equivalent to psi. The psi conjugate is psi, so it will not matter. So you can just change the order of this thing, and you can have BA psi. You can also write it like this. And for the imaginary scalar product also, the property can be written as, if you are only interested in the imaginary values, so you can have in the denominator imaginary values, which will cancel them and accordingly, or which will to iota psi I. So in the shorthand form, it can be written as modulus of A, this bracket of AB psi 2 iota. So now here's the point. So absolute value of any complex number is greater than or is equal or greater than the absolute value of its imaginary part. So it's greater than or absolute value of its imaginary part. So the last one you can write it as uh, so you are going to use this one. So you can write it as delta psi E into delta psi B is greater or equivalent to bracket of B. So in a sense, we have arrived at how we can have answered, how we can formalize uncertainty relationship in terms of if we have used two operators A and B operative on a function psi. So if you have a pair of operators xp equivalent to iota h for any state, then delta psi x into delta psi p will be, if it's iota h, it will be greater than h over 2 pi. So this is, sorry, 2 h over 2. So if it's h, iota it's imaginary, so you can have it, you can represent it like this. So which is in the popular language also called Heisenberg's uncertainty relations. So what we have done here is we have shown the operator correspondence of the same and using Schwarz inequality that we can state it in terms of operator formula. This thing and this inequality who just following this inequality. Now there are other things also. For example, we are going to use further some of the properties and see. So if we have a general understanding of matrices and eigenvalues, eigenvectors, and this orthonormal basis, orthogonal. So these are things. But the thing is that if it's you are representing there are matrices and there is some trace part of the things. So how can you say, for example, for some operators, A, we may define a number called trace. We may define a number called trace. Which is written as trace of A. So the trace is introduced. Trace is defined by introducing orthonormal set of basis vectors psi I. So trace is written as So trace is written as is defined as orthonormal set of basis vectors psi. So if it's the way we define trace, so and the definition is useful because it exists independent of the choice of the vectors. So for any orthonormal, if we have any orthonormal basis of set of basis vectors phi, then A of psi can be written as an operator. A of psi can be written as, so it's on phi, so we can have J, it's phi, so we have phi there, A of phi. Or you can also have phi j, it's phi j, or If you want to write it in terms of psi, you can write it as phi j a psi of I and phi I phi j. Can write it like this. So you can see it here. Phi I ag psi I, phi I phi j. So phi j is this thing. So it's phi I a psi I, phi I a psi I. Phi I a psi I. So it's a this vector of this thing. So you can see it from this. You can have it, and you can also have it from this thing. Psi I can be written as. Sorry, maybe I'll just add it again. So for orthonormal basis vectors, we can write a psi can be written as phi j a psi I. A psi I can be written as phi j a psi I phi j. It's phi j, it will not, so it will be a psi I phi j. It will be this thing, a psi I phi j. For an orthonormal, you can write it like this. It's basically C, G, and G. One. Yes, you can write it like this. Now we know we are going to use two identities. We know a psi yesterday also. This eigenstate is equal to the eigenvector. This thing, and using this thing, one. So using this thing and using this thing in this, we are going to see. So trace of A can be written as so a psi I, we are writing this, and psi I, we can write this. So you can write it, trace of A can be written as, I and G are there. It's phi j a psi I and psi I phi j. So it's so now we have I and J. So we are going to write trace of A as psi of A psi I. Psi of A psi I. So A psi I, we can write it like this. A psi I. Psi I A psi J. Psi I A psi J. Psi I A psi J. Trace of so psi I can be written like this. So we first like A psi can be written as like this. This phi I is J, and psi I is its own, and phi j. So can we write it like this? So we have done nothing. We have used this identity, and this identity and this identity. And basically trace of I, and basically we are substituting psi and a psi j from this and this. You can write it like this. And there may be some obvious properties of trace that we are going to see, that the properties of the trace as we know them, especially you are going to have a matrix with the diagonal elements. So in the sense that trace of but the diagonal elements here, it may be part of those operators. And so here we have operators A and B. That's why there are I and J. So operators, how they will translate these properties of trace in terms of those operators. This may be scalar with operator A. This may be another scalar with operator B. So we have alpha times scalar can trace of A plus beta times trace of B. This is more property, you can verify it, or trace of A diagonal can be equal to trace of A conjugate. So you can see it. So this is another property. Now here, now if we have trace of A of B, trace of A of B, that will be equal to psi of I, AB psi I, psi of I, AB psi of psi of. So we have, because here we had only one operator. For example, now we have two operators. In the product of two operators. So we can write it like for ing, it can be written as, if we have psi I psi j, psi I psi j, if you write it in terms of psi I psi j, so here it's only I. But if we introduce both I as well as j, then we have psi of A, so it can be written as psi j, b psi j, and further b psi I, further b psi I, psi I, a psi. So this is like psi I, a psi j, psi j, b psi I. So you can see it, switch it if you have psi of A, so it's in a product. If you change it in terms of I and J, then we can, if we switch it, so we can just change it psi J, B, psi I, psi I, A, psi I. So if you just flip it this to this, or we have flipped this to this, so we can say that trace of AB is equal to trace of B of A. So it doesn't matter the order of these operators which are inside the trace, that should not change the total identity. But not all operators have traces. And this is an important point. If all operators do not have traces, then what? So space of, so if all operators do not have traces, then what we can see is so the trace of unit operator being 1, so which is the dimensional. So not all operators have traces. So this is another thing. Have traces. So this is an important point. So if all operators do not have traces, so this will speak something about the dimensionality of the thing. So if there are infinite dimensional whether Hilbert space, if we construe them as infinite dimensional Hilbert spaces. And so what it has to do with not all operators have traces, or some of the operators will have trace 0, and it will lead to some sort of contradiction. For example, in case of a commutation relation, xp is iota I, h, this is identity, this is a trace, gives contradictory results. This means IH trace of 1. So if a space having this commutation relation satisfying this commutation relation, it will have a contradictory result that trace of 1 is equal to 0. So which means that Hilbert spaces of these commutation relations can only be realized in the infinite dimensional Hilbert spaces. And the traces do not exist. That's the point. So for infinite dimensional Hilbert space, if we take it that way, the traces cannot be defined as such. Now what we can do is we can have construct also operators. We can construct operators from two state vectors. And see accordingly in the and if for two state vectors psi and this rho, and we may define a linear operator psi rho dagger. It's also known as diad. Such that for any arbitrary state vector phi, the operator gives psi of rho dagger phi is equal to psi of rho into phi. So you just keep it outside and you just flip it here, the conjugate property dagger will be equal to rho phi. So this is one property. So the adjoint of diad is a diad. For example, the second property here, just see, is adjoint of diad is diad. Means psi of rho dagger will be equal to dagger it will be rho, but it will change its position from this. So you can write it like this. Rho psi dagger of this one. So for arbitrary state vectors, so the product of psi dyads can be psi 1 rho 1 dagger, psi 2 rho 2 dagger, operating on phi. It will give rho 2 phi, psi 1 rho 1 dagger, psi 2. So it will be rho 2 phi, rho 1 phi 2, rho 1 psi 2, sorry. Psi 2, psi 2. So We have psi1, psi2 here. So psi1, psi2 here. Psi2, psi1. So you have different combinations of psi1 and psi2 in terms of these relations. So these identities should also work for these diodes. We are only just flipping the things and seeing the things. So for another diode, so for psi1 rho 1 dagger, psi2 rho 2 dagger, it can also be written as rho 1 psi2, and then you will just have conjugate of this. It will be rho 1, it will be psi2 dagger, it will be psi2. It will be psi2, psi1 rho 2 dagger. So can it be? So if you have dagger, if you have psi1 rho 1, that's fine. Rho 1 psi2, psi1 rho 2 dagger. Okay, I can write it like this. So for the normalized state vector, the diode 5 dagger, so we can have it's the Hermitian conjugation of its own square. This means 5 dagger. So such operators are called as projection operators. Such operators are called projection operators. And you can say the eigenvalues of the projection operators you can have, since we normally call it idempotent property. So if projection operators have this property, you can say that eigenvalues, if the eigenvalues are represented by lambda, then lambda square is equal to lambda. Is either 1 or 0. So the projection operator, phi dagger. It represents an observable. And that can takes any value. That can take any value in the state represented by phi. Such that sum of corresponding projection operators at an end should give us phi dagger should give us 1. So operator A with eigenvalues ai and a complete set of orthonormal eigenvectors phi can be expressed as E for complete. So here we have, if you remember, phi 1 a1, phi 2 a2, the same. So if complete set of orthonormal this thing can be for the projection vectors can be written as phi I dagger. Now what we are going to see, and for a polynomial function of an Hermitian operator, we can write it as sigma A P A phi I phi I dagger. And if you want to write it in terms of eigenvalues for any function, finite eigenvalues f of a can be written as f of ai phi I phi I dagger. Now here it's here how now we can introduce probabilities in this entire discourse. The way yesterday we tried to introduce Born probability as an idea mathematically, and in this formalism, or in this how to clothe this formalism for state vectors, individual state vectors or two state vectors, this operator state vectors, this diode formalism. But we can also how we can introduce probabilities in this entire formalism. So what we are going to do is like this. So for example, in quantum mechanics, probability nature of this in quantum mechanics, this probabilistic state vectors, how the vectors which are probabilistic, how they come into consideration. So psi n wave function may be normalized, but it may not be necessarily orthogonal. So it may have different probabilities, different linear combination of those states, but the total should at the end give one. So we'll use another thing, something called which is also used in statistical mechanics, quantum statistical mechanics. But here, since we are studying in terms of basic how can formalize mathematical way of formalizing quantum mechanical things, operators and state vectors aside, how we can formalize them. So we introduce something called a density matrix. So it's not a typical matrix you might be aware of, but it's sort of also as a it's also sort of operator, but we can see they are sum of projection operators with the coefficients of the probabilities, which rho being given as probabilities, sigma n probabilities and psi n. So the way we have introduced Born probabilities, you can also introduce how we can have expectation value of observable. So which is represented by arbitrary Hermitian operator E. So it's the arbitrary sum of these Hermitian operator A, these different expectation values, which is sort of statistical. It's weighted sort of. We have individual states which are psi n weighted with probabilities. So here states are related mapped. States can be identified with how they have probabilities of those states in consideration, such that this E operator can be written as probability of psi of En. So inner product of so it will be equivalent to trace of A times rho. So you see, so we have this trace which we have seen it. So that this A, it's also a sort of operator, but it's an operator. This trace, this operator, it has the properties of an operator. It may be a part of one function, two functions. So operator, it's an operator. We have defined operator in terms of trace of this thing, trace. And rho we know, and rho is this. And in this is A is operator. In this rho is the probability, the weighted function of the probability, which is averaged out over different states. Or you can say it's the physical properties. Another way of saying is physical properties of statistical ensembles, of statistical ensembles of possible states, which are characterized by the density matrix of the ensemble. Matrix of ensemble. So So for a complete set of orthonormal eigenvectors phi I with eigenvalues pi, so rho can be written as phi I tag. Rho can be written as sorry, this is the I said rho can be written like this. And pi can be greater than or the probability which we are 0, such that for a unit trace, trace of rho is 1. So Pn is equal to 1. So we are going to calculate the expectation values concerned. So it's basically in quantum mechanics we are calculating or rather we have a knowledge how the system can be expressed in different ways. The expression of system in different ways can be expressed in different ways. Or the expression is basically you are defining the probabilities is on that the system is in different set of states. Now the another important thing is that if the system is, for example, this S rho can be written as also, if you want to write it in terms of pure state, which is also known as von Neumann entropy, S2 can be also written as KB. So if you want to use since we have this quantum statistical language of quantum statistical mechanics, or we are going to use this thing, how we can write this operators there. So we can also say that this SO, if you want to have the thermodynamic parameters, so you can also write it like this as rho log of rho, or KB sigma pi log of. So it's a sort of it's a sort of not necessarily required, but you can say you can study these operators, projection operators or density matrix as a sort of operators, we can also represent them like this. For pure states, it will come out to be 0. Uh, for pure states, Pi will come out to be unity, and this Si will be 0. And for states which are not pure, then S is greater than 0. So it will basically correspond to those in those matrices how the these for pure states the diagonal elements the operator they will come out to be 0. For non-pure states the it may not the total will not come, sum will not come out to be 0. So we stop.